Welcome to the last aspect of quantum mechanical harmonic oscillator in lecture 23. Today we are going to discuss about the tunnel effect, which is not observed in classical physics, but it is a characteristic feature in some of the quantum mechanical system. So let's come back to the discussion of the harmonic oscillator. So according to the equation here, depending on the values of n, so n could be 0, 1, 2, 3, etc. We will have discrete energies and discrete energy level. All right. So, and for n is equal to 0, the level that I have drawn, then E0 becomes, if we put n is equal to 0, it becomes h cross divided by 2 the root over of k by mu. So now we can think about that for n is equal to 1, 2, 3, we have these discrete energy levels. And remember, the value of x, that means the displacement in quantum mechanics, is considered to be from minus infinity to plus infinity. So now the question is, then why do we draw such parabolic curve here? So remember, those parabolic curves define the classical boundaries of the oscillator if it behaves classically. So that means what? So that means, suppose for n is equal to 0, the energy is E naught. Okay, here this is the energy level E naught. Now if you think that if the diatomic vibrator, if it, suppose if it behaves classically, then what would happen here at these 2 points? So these 2 points means whenever the oscillator, suppose this is the oscillator and it is stretching, so for n is equal to 0 means for an energy corresponding to E naught, so these two stretch to a certain value. Okay, and we can call this maximum displacement. Okay, and this maximum displacement is nothing but its maximum amplitude. Would you agree? All right, so that means whenever the classical vibrator reaches its maximum amplitude, what happens here? So here it's whatever its potential energy becomes its total energy. That means at maximum amplitude, you think about that pendulum or think about that vibrating string that oscillates up and down. Whenever it reaches its maximum amplitude, its kinetic energy becomes 0. So whatever potential energy it has, it represents the total energy En. So here itself here, so whenever it reaches at these two positions, we can assume that its potential energy, what is its potential energy? So the potential energy then becomes half k. Instead of x, we take the maximum amplitude as a, half ka square. So this becomes its total energy. So total energy means this, h cross divided by 2 root over of k mu for n is equal to 0. All right, so now let's see some interesting situation. So we are going to find out the values of these a. All right, so what we can do actually is, now we can take a square is equal to, so these two cancel out. We have h cross divided by k root over of k divided by mu. All right, so and then we have the a value, or a is equal to, we can take this h cross divided by k root over of k divided by mu whole to the power of half. All right, so now remember, we define all the wave functions, the solutions, in terms of alpha. Okay, so alpha is a constant which is defined as root over of k mu divided by h cross square. All right, so this term now I can easily term, means after simplifications, this would come down to alpha to the power minus half. So you can verify it. You can take the value of alpha and put it over there and you can verify it, or simply we can do it from right here, that this is equal to h cross divided by root over of k mu. All right, so this way the amplitude is defined as alpha to the power minus half. So what we can define here as this point, the value is minus alpha to the power minus half, and at this point the value of the amplitude is positive alpha to the power minus half, and this is minus infinity, and this is towards this is we have the plus infinity. Okay, so now the question is, for classical mechanics the oscillator do not expand, or it, since it is the maximum amplitude here, so beyond these 2 points you won't be able to find the atoms are stretching. So this is according to the classical model, but according to the quantum mechanical model, there should be some probability of these atoms going beyond this classically defined maximum amplitude. All right, so the question is, how much is the probability between these zone, means between minus infinity to minus alpha to the power minus half, and from plus alpha to the power minus half to plus infinity. Okay, so let's erase this blackboard and let's pose this question. Okay, so let's do that. So if we try to find out the probability of the oscillator's displacement, means the quantum mechanical oscillator's displacement exceeding its classical value, then we can define this p value probability is equal to from minus infinity to minus alpha to the power minus half, the probability density function px dx, plus then we have minus plus alpha to the power minus half to plus infinity px dx. All right, so is equal to, so now what is px dx? Okay, so that's the question. So for we are considering for n is equal to 0, for n is equal to 0, px dx is basically, as you remember, that psi x square dx. All right, so this becomes is equal to pi by alpha root over of half into e to the power minus alpha x square dx. All right, so that was our consideration. So I made a mistake, so sorry, this is would be alpha by pi. So this is alpha divided by pi, and this. Okay, so now you see that this is an even function. Okay, so because this is an even function, so we can easily write it as twice of alpha to the power minus half to plus infinity px dx, or in other words twice of, we can write this part alpha by pi, which is the constant part, from alpha to the power minus half to infinity, and we have e to the power minus alpha x square dx. All right, so the thing is, this is an integral and there is a certain method to evaluate it. So if we evaluate it following the proper method, this would be a finite non-zero value, and this has been calculated to be 0.16. So that means what? So that means that there is a finite probability that a quantum mechanical oscillator's displacement can exceed its classical limit. So that effect is called the tunnel effect. All right, so means it is defined as the phenomenon where a quantum mechanical system exceeds the limits which is defined by the classical mechanics and going into some forbidden area which is demarcated by classical mechanics. It's called the tunnel effect. And not only in quantum mechanical harmonic oscillation, there are other fields like the radioactivity, or so the field emission of electrons from metals, that which you will learn later. These are all these all can be explained in the light of the quantum mechanical tunnel effect. All right, so now probably this makes sense, that why when we drew the psi versus this is x is equal to 0, and we have say minus infinity to plus infinity, and for we can, whenever we write n is equal to 0, whenever we draw the psi versus x the amplitude function, you remember that we had written something like this, okay, the amplitude function. So you see that this is exceeding beyond these two limits. Okay, so this makes sense now, because now this can be explained in terms of the tunnel effect, and in terms of probability also. You will find a finite probability outside these classically defined limits. All right, so now next let's just take a look that what is the practical outcome of this tunnel effect. All right, so let's take a look into that. So now let's like to mention again that the classical harmonic oscillator, its amplitude A is fixed, okay, and for quantum harmonic oscillator the amplitude is not fixed, it is variable. So what happens is, then x square average that we have already found out, the x square average is here, and we have already calculated, and this is definitely for n is equal to 0. So for n is equal to 0, the x square average is this. So here x square average is the measure of the square of the amplitude. All right, so if I want to measure the average amplitude, then we actually we take the value, it's called amplitude RMS, or root mean square amplitude, which is equivalent to the root mean square displacement, and it's taken simply as the square root of the average of the square of the amplitude. All right, so we already knew that average x is 0, so that is useless for us, so we can't use the average of x. Rather, we take something which is a non-zero value, that is the square of the amplitude, and we take the square root of it, so that's called the root mean square amplitude. The same thing would appear, similar kind of thing, the root mean square concept would be appear in AC voltage, where we talk about root mean square voltage. So basically this value comes with the statistical significance, so so this has a statistical background. So anyway, so the root mean square amplitude is this, and interestingly the theoretical frequency of a vibrational line obtained from IR spectroscopy can be calculated by this. So here there is the equation, it's called nu bar observed. So nu bar is in centimeter inverse, so the calculated frequency of an IR signal in centimeter inverse can be given by 1 over divided 1 over 2 pi c is the speed of light multiplied by root over k by mu. So k is the force constant, mu is the reduced mass. So this formula you must have seen before, or if not, you will going to study in the infrared spectroscopy or vibrational spectroscopy. So that's how we can theoretically predict the frequency of certain vibration. So here, since we have root mean square amplitude is equal to, we can write that it is the root over of, that means half of h cross divided by root over of mu k whole to the power half. So here we have the value k. All right, so we can actually translate this value of k in terms of new observation. So if we try to replace this with this k, it would simply turns out to be something like that. So I can directly write it over here. ARMS is equal to we have h cross divided by 4 pi, and we have c, speed of light, nu bar observed, multiplied by mu whole root over of half. All right, so this is the value for the root mean square displacement or the root mean square amplitude. So we can take an example of here. So H35Cl, so this is the normal isotope of chlorine. So if we take that, all right, so what is its vibrational frequency? So its vibrational frequency, that means nu bar observed, is given as 2.95 multiplied by 10 to the power 3 centimeter inverse. Okay, so you at that frequency you will observe the stretching vibration for HCl. All right, so the thing is, now if we calculate the ARMS, so the ARMS for HCl, means normal HCl, would give you a value of around 7.67 picometer, whereas the normal HCl bond distance is equal to 127 picometer. Okay, so you see that this distance is about less than 10%, around 5 point certain 6 point certain percent. So that means what? So that means the equilibrium, so just look about here, so HCl, okay, so we have the equilibrium bond distance. So whatever the bond distance we calculate, 127 picometer, that is the equilibrium bond distance obtained from experimental measurements. So this distance, okay. So now, due to quantum mechanical tunneling, this distance means at its ground state it can stretch up to a certain value, so which is it can go up to 7.67 picometer, or around 6-7% of its total bond length. It can stretch up to in its ground state. All right, so this is the practical significance, and of course we can predict, given a bond distance and using this formula, or given the new observations from this formula, we can calculate ARMS for many different diatomic molecules. Okay, and then we can easily find out that what is the root mean square displacement, okay, on top of its equilibrium bond distance. So that's what the major significance of the tunnel effect of quantum mechanical harmonic oscillator. So with this we have finished our chapter 5, or the harmonic oscillator, and from the next chapter onwards we will move into the three-dimensional systems. All right, so please keep studying, and we will see you again after a short break. Okay, stay put, stay safe, and till then, goodbye.